A great help to understanding chemical reaction is found in Chapter 7 in your ability to classify a chemical reaction. Chemical reactions generally fall into the following classes: a precipitation reaction, an acid-base reaction, a gas evolution reaction, oxidation-reduction reaction, and combustion reactions. We'll learn more about these types of reactions. Many chemical reactions occur in solutions, so that types of particles that exist in solutions are important. A compound is soluble if it dissolves. A compound is insoluble if it does not dissolve. An aqueous solution is a homogeneous mixture of a substance with water. That means it's the same throughout, and it's a mixture because you can have 2 tablespoons of salt in a glass of water, or 3. You can vary the amount. When ionic compounds dissolve in water, they usually dissociate, break up into their component ions. For instance, aqueous solution of sodium chloride dissolves in water, and you now have separate sodium ions, the smaller positive ion, with chloride ions, the larger negative ion. Substances that completely dissociate into ions in solution are called strong electrolytes. The term electrolytes means that they will conduct electricity. What do you need to conduct electricity? You need ions that can move, and that's what's needed. So pure water does not conduct electricity because there are very few ions in it. However, solutions conduct electricity. Sodium chloride, for instance, will cause the light bulb to light very brightly because the electricity can get across the solution. These are strong electrolytes. Aqueous solutions, another example is silver nitrate. All nitrates are soluble, so we expect to find silver ions and nitrate ions in solution. And these are ions. So they will, even though the polyatomic ions stay together in a group, they're the negative part, and the silver ions are the positive part. So this is a strong electrolyte. However, some substances do not dissolve. For instance, silver chloride remains a crystal. It will not dissolve in water. So it does not produce silver ions and chloride ions, at least not very many of them in a solution. So in order to describe precipitation reactions, we have to know which substances do not dissolve, which substances form insoluble compounds and form precipitates. There are solubility rules that you should know, and they're not very complicated. Basically, we have any of the group 1A elements forming a compound, they're all soluble. Or all nitrates and acetates are all soluble. And most of your chlorides, bromides, and iodides are soluble, except those of silver, mercury, and lead. And the sulfates are mostly soluble, except those of strontium, barium, lead, and calcium. Other substances are mostly insoluble, unless they happen to have the metal part being one of the alkali metals or the alkaline earth. Here's a flow chart that might help you to decide if something is soluble. We can ask ourselves the question, is magnesium iodide soluble or insoluble? Well, we start up here and we find out here's the iodide part. So does the compound contain silver, mercury, or lead? No. It contains magnesium, and so magnesium iodide is soluble. Or here are compounds that are mostly insoluble. We might ask ourselves the question, is calcium carbonate soluble or insoluble? Well, we look across the top and we see here's the carbonates. Does the compound contain the group 1A, lithium, sodium, potassium, or ammonium? No. Therefore, it is insoluble. Precipitation reactions do not always occur when mixing two solutions. When potassium iodide, the aqueous solution, is mixed with sodium chloride, the aqueous solution, you get no reaction. Nothing happens. No precipitate is formed. However, you take potassium iodide, aqueous solution, add lead nitrate, aqueous solution, you get a precipitate. You get yellow lead iodide. Plus, you still have potassium and nitrate ions in solution. You could check and see that lead iodide is an insoluble substance. Before mixing potassium iodide and lead nitrate, both dissociate into their respective ions. Then, when you mix them together, the lead ion and the nitrate ion, they're all present, and then the instant they're mixed, they react, they exchange. For instance, the potassium, the lead goes to the iodide and clumps together, forming the precipitate. This remain ions. We know that this is soluble, so it does not stay together, but this is the insoluble precipitate. So if the potential insoluble products are both soluble, then no reaction occurs. If one or both are insoluble, then you get precipitate. In the case of potassium nitrate, is soluble, but lead iodide is insoluble, so you get this precipitate. How do you write an equation for precipitation reaction and see if they occur? Well, you write the various substance, the aqueous solutions, and then you exchange the ions. What happens if the copper goes with the carbonate and the sodium goes with the chloride? Well, then you have to ask, is sodium chloride soluble or insoluble? Well, it's sodium, alkaline earth, so it's soluble. However, copper carbonate, this would be copper 2 carbonate, is insoluble. The potentially insoluble substances are these two. And we know that sodium chloride is soluble, but this is insoluble. So we have to write that as a product that is a precipitate. Again, if all the potential insoluble products are soluble, then there is no reaction. This is the easiest equation to balance. But we have to write the insoluble one as a solid precipitate and the soluble one as aqueous in this case. Then after you do this, you need to balance the equation. You have to adjust only the coefficients, not the subscripts. Subscripts changes what it is. And from looking at this, you can see that there's one carbonate, and you can keep this group together. And one of those, one copper and one copper, 2 chlorines, so you have to put a 2 in front there, results in 2 sodiums, which agrees with that. So this is the balanced equation for this precipitation reaction. In balancing these reactions, it's nice to know that generally you can keep the polyatomic anions together. What kinds of equations are there? Well, there's a molecular equation, which, because this is soluble, it's really silver ions and nitrate ions, but in the molecular equation you keep it together and say aqueous. That's the molecular. Then you can write the ionic equation, which you can show that this silver nitrate dissolved is really silver ions aqueous, and nitrate ions aqueous, and sodium ions aqueous, and chloride ions aqueous, and forming silver chloride precipitate solid. Again, sodium ions aqueous and nitrate ions aqueous. When writing complete ionic equation, you need only separate into ions those that are soluble. Don't separate those that are solids, precipitates, or liquids, or gases. So writing equations for reactions and solutions, you can write complete ionic equations and net ionic equation. For instance, you notice that you have silver ions over here, but you don't have them there. You have nitrate ions here, and you have nitrate ions as a product. These are spectator ions. Nothing happens to them. Same way as sodium. So if you're going to do the net ionic equation, you needn't show the spectator ions. And the net ionic equation for this reaction, this precipitation reaction, is the 1 silver ions combined with the chloride ions to form silver chloride precipitate. This is the net ionic equation. Summarize molecular equations, the chemical equations showing the neutral formulas for every compound. And you can show whether it's in solution by aqueous or solid. Complete ionic equation shows all of the species that are actually present, either as aqueous ions or solid precipitates. Net ions gets rid of all the spectator ions and just summarizes what only the species that actually participate in the reaction. Here's an acid-base reaction. Here's the acid. It has the hydrogen in the positive part and the chloride negative. Here's a base. It has the hydroxide as the polyatomic anion. We have the exchange. We have the hydrogen going with OH to form water, H2O, and that's a liquid. It's not an ionic compound. But then we have salt, which is aqueous, a soluble ionic compound. Acid-base reactions are also called neutralization reactions. They generally form water and an ionic compound called a salt that usually remains dissolved. The net ionic equation for many acid-base reaction is the hydrogen ion combining with the hydroxide ion to form water. Here are some common acids you may remember from our acid nomenclature. Hydrochloric, hydrobromic, those are the binary acids. The oxyacid, nitric acid, sulfuric acid, perchloric acid, and acetic acid. There's a hydrogen with the acetate. Bases: sodium hydroxide, lithium hydroxide, potassium hydroxide, calcium hydroxide, barium hydroxide. Group 1, Group 2A. What are some kinds of compounds that undergo gaseous evolution? Well, the sulfides. If they get a hydrogen, they form H2S, which is a gas. Smells like rotten eggs. The carbonates and bicarbonates usually form carbon dioxide and water with acid. Again, you can get sulfur dioxide. And the ammonium is also a gas, ammonia. Gas evolution: acid plus K2S forms that gas. Acid plus this forms carbon dioxide, the fizz in pop, etc. Gas evolution reactions: by writing a skeletal equation that includes reactants and products that form when the cation of each reactant combines with the anion of the other one. It looks like this. Nitric acid, sodium carbonate. We'll put the hydrogen with the carbonate and the nitrate with the nitrogen. So we end up getting this compound and that compound. Is not balanced because you need 2 sodiums. You need to put some, you must recognize that, but you need to recognize that H2CO2 carbonic acid really breaks up into water and carbon dioxide to gas. So you could write it this way, breaking this up into what it really is like. Water, and finally you have to balance this reaction because you see that you had 2 sodiums. You need to have 2 that produce 2 nitrates, so you need to have a 2 here. And we check out our carbonates. Carbons 1, 1. Oxygens 2. 2 times 3 is 6. 7, 8, 9. 2 times 3 is 6. 7, 8, 9. And hydrogen 2. Hydrogen 2. Balanced. Oxidation reactions involve the transfer of electrons, called oxidation-reduction reactions. We'll not delve into this very much, but they are responsible for batteries, rusting of iron, many other kinds of reactions are oxidation-reduction reactions. A fundamental idea about oxidation-reduction reaction is oxidation is the loss of electrons, and if something loses electrons, something else gains electrons, and that's reduction. Some people use these mnemonics. Oil rig. Oxidation is loss. Reduction is gain. Oil rig is probably used in Texas more than any other state. Many other people say Leo the lion says grr. Leo, loss of electrons, oxidation. Grr, gain of electrons, reduction. Notice that oxidation and reduction occur together. In general, redox reactions are those in which react with oxygen, or a metal with a nonmetal. In general, where you transfer, say, electrons from the metal to the nonmetal. Metal is neutral, then it gives its electrons, becomes a positive ion. Combustion reactions are a type of reaction that's characterized by reacting with water. They're usually exothermic, that is, they give off heat. Compounds containing carbon and hydrogen always produce carbon dioxide and water on combustion. Another way we can study chemical reactions is classify chemical reactions by what the atoms do. Synthesis is a combination. You start with 2 substances and you get 1. That's synthesis or combination. Decomposition. Start with 1 substance and get 2 or more. Displacement. A was by itself, BC was in a compound. Now we have A joining with C and B. B by itself. That's displacement or double displacement or exchange of partners. A now goes with D and C now goes with B. You got to keep the positive part first. So in synthesis, simply 2 substances combine to make a more complex substance. Like sodium reacts with chlorine to form sodium chloride. Decomposition, something that was together, like water. You pass electricity through it and you get oxygen and hydrogen gas. Simple replacement. You have zinc by itself reacting with a solution of copper chloride. Now you begin to see the color of copper and zinc in the solution. Double replacement we've looked at before. Exchange partners. So the classification is summarized here. It's either synthesis, decomposition, single displacement, double displacement. So in this chapter we need to be able to identify a chemical reaction, write balanced equations, see if a substance is soluble, predict precipitation reactions, write complete ionic and net ionic equations, write equations for acid-base reactions, identify redox reactions, and write equation for combustion, and be able to classify these chemical reactions.